Okay, so starting a new book here. So we're in Foundations. Well, it's this book right here, and I've abbreviated it in the title for this collab sheet, but it's a very good book. If you want to learn about generalized linear models, this is a very good book to learn it from. So Foundations of Linear and Generalized Linear Models by Agresti. So we are just in chapter 1, question 1.1. So this, I will generally assume that you have been reading the book along with me. So here we go. So question 1.1 says that's suppose that yi, so our outcome variable that we've measured, and I denotes one particular observation of that variable, has a distribution that is normally distributed with mean mu I, right? So in other words, what do we expect this particular observation to be? So that's why it's mu I and sigma squared for the variance. Okay. So we want to formulate a normal linear model as a special case of a generalized linear model, specifying the random component, linear predictor, and link function. So just a quick overview of some of this language. So a normal linear model is a special case of a generalized linear model. And so a normal linear model is a generalized linear model that assumes basically this, that our data, or the error of our data, is distributed normally. Okay. A generalized linear model generalizes this particular assumption to where the error component of our data, of our outcome data, of our outcome variable, could be several different types of distributions. And so maybe you're familiar with some of these, so maybe binomial or Poisson, or there's others, but that's the difference. Okay, so now this textbook has some answers in the back of the book, which is always nice. And in fact, the reason that I do these videos is because of just a little bit of frustration of how many textbooks are out there where you can't access the answers, and so it's very hard to practice. And this one gives some answers, and so here's the answer to the first question, okay? And so you can read this for yourself, and the answer is correct, but if you were learning generalized linear models from this book, you would have no idea what any of this means, and that's because theta and phi and let's see what else we have, some functions of these parameters. None of this is addressed until chapter 4. So this is a right answer, but it is not a good answer for what we've learned so far in this book. So I'm going to just try to answer just given the information that is provided in chapter 1. Okay. So we need to specify a random component. So the random component here is given here. Okay. So y is distributed normally with a mean and sigma squared. I could also have written this y sub I, so one particular observation, is distributed normally with a mean mu I, so the expected value of that particular observation, and then a standard deviation or a variance. Okay, so that would also be equally valid. Okay, so there's my random component. Just a quick aside: if it's not clear why this is a random component, okay, so well, actually, let me come back to that. Okay, so now we have the linear predictor. So a linear predictor is going to generally be written like this: x beta, and sometimes this will just get shortened to eta. Okay, this little symbol here is called eta. So x beta equals eta. So sometimes I'll just use eta just for shorthand. Okay. So here x is data that we've measured, and in fact, when you just write a big capital X like this, it's a matrix where each row represents the data for one observation, and then each column represents a variable that was measured in that observation, right? So for instance, if I was measuring, let's say I had 10 people and I measured their height and weight, well then X would be a matrix that had 10 rows, one for each person, and then 2 columns, right? One for each measurement. Okay, now let me just continue to confuse you. In this, it will often be the case that x beta, or I'm sorry, that x will actually have one additional column. and that will be for an intercept. So don't worry about it right now if that doesn't quite make sense. But X will often have one additional column as an intercept. So, but don't worry about it right now. Okay, and then finally the identity link function. So it specifies that we should be using actually it doesn't say that we should use an identity link function, but we are using an identity link function that is what's called the canonical or the typical link function that is used, okay, with normal linear models. Okay, so so the identity link function, well, okay, what is a link function first of all? So a link function takes the expected value of your output and then transforms it, and it transforms it in such a way that it will equal my linear predictor. Okay, so it will equal this here. All right. So the identity link function is one that does not touch the contents. So in other words, g of the expected value of y, or g of mu, same thing, is just equal to the expected value of y, or equal to mu. All right. So in other words, the identity link function does nothing to the expected value of the outcome. Okay. So altogether, the model will look something like this. So we specify a random component. We specify the linear predictor right here, and we're also specifying the link function. But how are we doing that? Well, by its absence in this case, right? So notice that there is no g of mu here because g of mu just equals mu, and so we don't have to write the link function. And so this implies the identity link function. Okay, let me go back to what I wanted to say a little while ago, which is, why is this the random component exactly? Okay, so this is a point that is worth keeping in mind. Okay, so when we're writing our linear models, whether it's a linear model or a generalized linear model, the linear predictor here is predicting the mean. Okay, and it does not matter if y is distributed normally or as a Poisson or whatever. Okay, the linear predictor is just specifying the mean, or at least the link function transformed mean, whatever. Okay, but with each prediction, each prediction of the mean, the data is going to be, some distance away from that generally, right? Our estimate of the mean is not going to be perfect. So there's going to be scatter around our prediction of the mean. And so the random component tells us how we expect the noise to be distributed, okay? So if it's normally distributed, then we should expect the error from away, right, the distance away from our mean to be, normally distributed. But if y was distributed as a Poisson, it does not mean that y is distributed as a Poisson variable, okay? It means that the error, the randomness contained in our measurements of y are distributed as a Poisson, okay? Okay, in which case the errors would look different as their distribution around any point away from mu, the expected value of mu, or the link transformed function of mu will differ. Okay. Anyway, that was not a great explanation without pictures, but maybe if you hear it now, as questions make it more relevant, it will become salient in future videos. Okay, that's it for this one.